All right. So, last lesson for the test over air resistance. Okay. So, by the end of this lesson, you'll be able to describe what factors determine how much air resistance on an object and describe and calculate situations in which an object reaches terminal velocity. Okay. So, to answer these questions, I want you to draw from your experience holding your hand outside of the car window. Okay. What two things would cause air resistance to increase? Okay. Spreading your hands apart. This is the surface area, specifically cross-sectional surface area, where this has less air resistance than this. This has less air resistance than this. Okay, does that make sense? What's the other factor that's going to cause more air resistance? Yes, velocity or speed. As you go faster, there's more air resistance. Okay with that? Okay, those two things, surface area, cross-sectional surface area, and speed. Good. You're running into air molecules. Terminal velocity. Don't know if you heard of it, but this is your max speed when falling. Your maximum speed, terminal velocity is your maximum speed when falling. And when does it occur? It occurs when air resistance equals the force of gravity. It occurs when air resistance is equal to the force of gravity. All right, so let's say we're skydiving out of a helicopter. I don't know why. Well, I do know why, because I want to start at rest, but that's not a really smart idea, but whatever. Start at, oh my goodness, I am struggling today. Start at rest. Okay, so I'm not worrying about going horizontal. We're just going to focus on the vertical. Okay, so forces acting on you is the force of gravity. Okay, how much air resistance? How much air resistance is acting on you right now? None. You're not moving. Good as that. So no air resistance at the beginning. But as you fall, you speed up. Your force of gravity, how much you weigh, has not changed. But because you're moving faster, air resistance starts to become a factor, starts to play a part of it. Okay. Well, you're still speeding up. as you fall, and because you're still speeding up, air resistance also increases. Does that make sense? What's happening there? Fall faster and faster, air resistance is acting more and more until will this increase indefinitely, or like at what point will it stop doing that? Yep. When your force of gravity is equal to the air resistance. So beforehand, so this, like some of the forces in the y direction not equal to 0. Okay. I'm going to make down the positive direction because we're not in free fall. There's air resistance. Free fall happens when only the force of gravity is acting on it. Okay. So I make down the positive direction. So I've got force of gravity minus air resistance is equal to mass times acceleration. Okay. When I reach here, force of gravity minus air resistance, if they're equal to each other, what is this equal to? 0. And how are you moving? How would you describe your motion when the sum of the forces in this scenario are equal to 0? Constant what? Velocity. Are you at rest at that point? That would be wild. Okay. So you continue to fall at your terminal velocity. Does that make sense? You max it out, like you're going as fast as you possibly can. And this happens when air resistance is equal to the force of gravity. Good with that? So, in the presence of air resistance, do all things fall at the same rate? Nope. Sorry, TV folks. So, what would cause something to have a greater or a lesser terminal velocity than something else? Ben? Surface area is one of those things. And, oh, yes, heard some. Mass, okay? Specifically, I'm going to say the weight, but mass, weight, okay? Force of gravity. Okay, looking at the weight, if you had a ping pong ball and a golf ball, both have the same amount of cross-sectional surface area, roughly. But the golf ball is going to fall a lot faster before it reaches terminal velocity than the ping pong ball. Does that make sense? Okay, because it weighs more. It's able to plow through the air molecules more than the ping pong ball. Surface area, humans can change their terminal velocity by the position they put themselves in. Like if you think about videos that you've seen of skydivers, they can orientate themselves doing a spread X, they're increasing the surface area and cause your terminal velocity to be less, versus if you like pencil it, you can fall a lot faster. You go a lot faster until your terminal velocity is a lot greater, because when you're penciled, your surface area is a lot less. You okay with that? Okay. All right. Here we go. Have a conversation. That works. All right. So this question, you didn't really need to be in physics class to answer this question. It's more of a warm-up question. Correct answer is the brick. Good. Brick falls faster than the feather. Okay. All right. Same scenario. Different question. Thumbs up when you have a guess. Tell your neighbor. Tell them why you think so. Correct answer is interesting. All those who say A, talk to all those who say B. Have a conversation. Find someone you disagree with.
You were thinking too much of it. Yeah. No, he definitely was. I know it did, but it's one of those situations where my logic is like fighting physics logic.
Correct answer is A. When it reaches terminal velocity, what is the force of air resistance equal to? Force of gravity, aka weight. Which one weighs more? The brick. Okay. Now, the feather is more responsive to air resistance, like it reaches terminal velocity way sooner than the brick does. But once they reach terminal velocity, in order for the brick to experience terminal velocity, air resistance has to equal the weight, which is a way more than the feather's weight. Thumbs up when you have a guess. Have a conversation.
Because, like, it's just a
That was me. I was like,
Okay, let me just steer this a little bit. After 1 second, you can assume that the feather is at terminal velocity, but the brick has not yet reached terminal velocity. Keep talking.
oh. You might be right. We could all cheat.
I feel like it's
not.
I feel like it should be A, but like it.
You drop a brick, so you drop a feather. 1 second, just 1 second. You think it's the same?
Air resistance. We give a scholarship.
All right. This ought to be interesting. What do we say? All right. So, feathers reach terminal velocity. So, its force of air resistance is equal to what? Its weight, which is a lot or not much? Not much. So, the brick has not yet reached terminal velocity, so we cannot say it's equal to its weight. Is everybody all right with that? Okay. So, if it's not equal, if it's not terminal velocity, like, oh, that's really hard to conclude. what two factors determine how much air resistance or will cause more air resistance? Surface area and speed. Which of these two has a greater surface area? The brick. Which of these two is moving faster after 1 second? The brick. So because both factors are definitively greater than the feather, we can definitively also conclude that the brick is still experiencing more air resistance than the feather. Correct answer is A. The brick is experiencing more air resistance. It's moving faster, has a greater surface area. Good with that? Okay. Okay, a real important distinction here. This last sentence. We have not yet reached terminal velocity. Thumbs up when you have a guess. Talk to your neighbor. Everybody good with A? It's a good warm-up question. Go faster and faster. Air resistance increases. Same scenario. Just different question. Thumbs up when you have a guess. Talk to your neighbor. Tell them why you think so.
No, spot. Save it for college.
No. Peabody, this wait, Mr. Smiley. This is next.
What?
Is this stuff gonna be on the test Friday?
Yeah.
Mr. Smiley.
What?
I thought it was next year.
No. You got this. You're good. We're good.
We usually like next year. Really? We're like next week where the test is
You'll be fine. All right. Here's a general strategy. Some people excel with conceptual questions, other people flounder. If you are one that struggles with conceptual questions, change that to a math question. Make up numbers. Okay? Yes, it takes time, but that's okay. I don't really care how long it takes you to do the test. Okay? If your brain thinks numerically, then you can go with that. So, we're starting at rest. I'm going to say force of gravity, 100 newtons. As she falls, her force of gravity is still 100 newtons. And let's say she has 20 newtons of air resistance. Okay. What is the net force on her right now? 80 newtons downward. What's her net force here? 100 newtons downward. Continues to fall. That goes up to like 60 newtons. Totally making these numbers up. But I'm doing it in a way that's realistic. The net force is what? 40. What's happening to the net force? Decreasing. See how I did that? If you're not sure of a concept, make it mathematical. Okay. Last question. Thumbs up when you have a guess. Converse amongst yourselves.
If I were jumping from a building, accelerate.
Oh, yeah.
Well, green. This is like right
I know.
Oh, it's absolutely
All right. What are we thinking? Got some C's. Got some E's. Got some A's. Ace. Okay. So, what is her acceleration at this point in time? It's just the force of gravity. 9.8 meters per second squared downward. So magnitude's 9.8. Once she reaches terminal velocity, what is her acceleration? Once she reaches terminal velocity, her acceleration is equal to 0. Starts at 9.8, goes to 0. Okay? Mathematically, her mass is not changing. The net force acting on her is what? Increasing or decreasing? Decreasing. That was the previous slide. Therefore, the acceleration is also decreasing. The thing that makes this problem challenging is if your understanding of velocity and your understanding of acceleration is still tangled together. Yes, she is speeding up the entire time. She's getting faster and faster and faster. But the rate at which she is getting faster is decreasing. Her speedometer looks like this. She's increasing her speed the entire time, but the rate at which she's increasing the speed is decreasing. You okay with that? Okay. All right. Got a test on Friday. Tomorrow, review worksheet is due. We will not have time to do a lab quiz this unit. On Friday, you'll have a test, but you'll also be turning in these labs for completion. Okay? You still need to understand them. Don't just copy somebody's to get the points. I'll own you on the test. If you're not sure, like I'm thinking both this lab and the spring scale lab, you'll turn both of these in on Friday. We talked about this one already. This one I'm assuming is straightforward, but if there's still confusion on what I wanted you to take away from this, please ask. Norquist.
Like number 4.
Oh, experiment 4?
Yeah.
On this one, assume that the coefficients are identical to the crate. So like the coefficients that you calculated for experiments 1 and 2 still hold true. Like reset the slider, the roughness slider back, like just reset the.
Yeah, I told you.
Okay. The spring scale lab, when I was absent, you're hanging the weights